Jeff Dean, thank you for joining us here in Sunday, San Diego, right in front of the NeurIPS Conference Center. You are the chief scientist at Google, co-tech lead of Gemini, and you all recently made an announcement about a version of the new TPU chip.
Yeah.
Let's talk about it. The seventh generation of TPUs.
Yeah. Yep.
What's special about it?
Like every next generation of TPU, it's better than the previous one. And, it has quite a lot of new capabilities. It has, it's connected together into these very large configurations that we call pods. I think it's 9,216 chips or something like that per pod. And it has, much higher performance, especially for lower precision floating point formats like FP4. So that's going to be really useful for training large models, for inference, for a lot of things like that. So we're pretty excited about it.
Nice. If zooming out, Google started building TPUs for their own internal needs. Google's preeminent AI applications company, AI research organization in the world, and the need for control of the full vertically integrated stack was the original motivation, as I understand it, if I've read about it, and then eventually externalizing access to those to be a global competitor in ecosystem of accelerator people who build and sell accelerators. And now there's a lot of people excited about the opportunity for there to be a massive market for TPUs. How do you relate with your role at Google to the objectives of Google's internal use of TPUs versus the marketplace that you're competing in to kind of compete and enable millions and billions of people outside of Google to get the advantages through reselling TPUs in the competitive space?
Yeah, the origin of the TPU program was really for our own internal needs, initially focused on inference. So as far back as 2013, we saw that kind of deep learning methods were going to be very successful. And every time we trained a slightly larger model with more data, the results got better in things like speech and vision. And I started to do some back-of-the-envelope calculations of what would happen if we actually wanted to serve this much better speech model that's more compute-intensive to, say, 100 million users for a few minutes a day. And the compute requirements got quite scary. We would actually need to double the number of computers Google had overall in order to just roll out this improved speech model.
Wow, yeah.
If we wanted to do it on CPUs. And so that was really the genesis of, hey, if we build specialized hardware that is tailored for these kinds of ML computations, essentially dense, low precision linear algebra, we could actually be way more efficient. And that was borne out. The first TPU ended up being 30 to 70 times more energy efficient than contemporary CPUs or GPUs, and 15 to 30 times faster.
And that was 2015, you said?
Yeah, so we started, the thought experiment was 2013. The chips landed in our data center in 2015.
Wow.
And we wrote a paper about it.
So it's a pre-transformer architecture.
Pre-transformer, yeah. So we actually were focused on speech recognition and kind of vision convolutional models at the time. We squeezed in a little bit of design change at the last minute in the TPU V1 to make it support LSTMs as well, which were kind of in vogue at the time for language modeling. And that also enabled us to support language translation tasks. And then subsequent versions of TPUs have focused much more on much larger scale systems that are not just a single PCIe card, but are a whole machine learning supercomputer, including the latest Ironwood one.
Yeah.
And every generation has been a big improvement in both energy efficiency, performance per dollar, all these things that we care about, and enable us to scale much larger training jobs, much more serving of requests to lots of users.
And of course, the transformer architecture itself, born at Google, pretty similar timeline, but with the TPU invented before that, and then the transformer architecture happening, do you think there was serendipity in terms of co-design between the applications of the transformer architecture as they've grown up to change the world as we know it now, and Google's access to this vertically integrated hardware stack?
Yeah, every generation of TPU, we really try to take advantage of the co-design opportunities we have with, having a lot of researchers thinking about where our, ML computations we're going to want to run, 2.5 to 6 years from now going, which is the exercise you have as a hardware designer, is trying to predict a very fast-moving field. It's not a very easy thing. But having a lot of people kind of seeing where the field is going, or, this kind of thing might be interesting. We're not quite sure yet, but we could put in this kind of hardware feature or this particular kind of capability. And if we did that and this turned out to be important, then we could have the hardware support there ready when that thing hopefully bears out, that it is an important thing. And if it doesn't pay off, then sometimes you've just devoted maybe a small piece of the chip area to this thing that turned out to be less important than you thought. But you really do want to be prepared for, if this thing matters a lot, your hardware can support it.
Yeah.
So it's a interesting forecasting exercise, is forecasting the whole ML field and trying to guess what we want.
Well, if we could let one person do it, Chuck Norris of computer sciences would get my vote, and has obviously enough votes that you are doing it. At Google, and with your track record at Google, there's a legacy of inventing things for Google's internal needs, Google being the world's best systems building company for the applications Google's built, which have now become many-headed. MapReduce and Google File System, something you co-invented or invented inside of Google. And then eventually you have been able to witness that what Google built and demonstrates to the world as value and then publishes with the TPU architecture. Obviously, the ideas in the transformer paper themselves, but now do you think that there's a tipping point with Ironwood for the rest of the world to sort of have access to the advantages that Google has had? And I would imagine, if I put myself in your shoes, this experience where it's like, that was awesome and we did it at Google and we paved the way, and now holy moly, the rest of the world is also getting all the benefits. Researchers think about impact, and that feels like the moment we live for to be able to have it. And I don't know if you feel like you're at the tipping point on the TPU moment.
Yeah, I think obviously we've been using TPUs now for more than a decade, or about a decade, and been really happy with them. And the co-designed properties really make them sort of useful for the kinds of machine learning computations we want to run. And we've also been renting them externally through our cloud TPU program for a number of years. And so many, many customers are using them for all kinds of things. We've built a bunch of software layers on top of TPUs that make them sort of quite convenient and easy to use. So you have, the most well-worn path for TPUs is JAX on top of Pathways, which is an internal system we've built that we're sort of working to see if cloud customers would want access to, on top of XLA, which is a compiler, ML compiler with a TPU backend. And so what this tends to mean, at least for Pathways, all of our Gemini development and research and training, large-scale training jobs run on top of that stack. And Pathways is this nice system that we built, starting about 7 years ago, that gives you the illusion of a single system image across, thousands or tens of thousands of chips. And so you can have like a single Python process running your JAX code. And instead of it showing up as 4 devices where you're running on a single TPU node, it shows up as your JAX process has access to 20,000 devices. And it just sort of naturally works and figures out underneath the covers exactly what transfer mechanisms to use and which network to use. It should use within a pod, a TPU pod, it should use the high-speed interconnect, and across pod boundaries, it'll use the data center network. Across metropolitan areas, it'll use long-distance links and so on. So we actually run, very large-scale training jobs where we have a single Python process driving multiple TPU pods in multiple cities.
Nice. Great. Well, maybe we can shift topics.
Sure.
You've been talking a lot, I think, lately about the state of funding for academic research. What's your message?
Yeah, actually, my colleagues Urs Hotzla and Partha Ranganathan and I, along with Magda Balazinski at the University of Washington, recently published one article in a whole special issue of the Computer Communications ACM that was devoted to the impact of academic research. And in our section, we discussed all the academic research that Google as a company was built on, all the things that we relied on in terms of like TCP/IP and, advanced risk processors and, the internet and the Stanford Digital Library Project, which is what sort of provided the funding for the original version of PageRank at Stanford.
Oh, yeah.
And my colleague Dave Patterson also had an article in that issue about all the amazing things that have come out of his and his Berkeley colleagues' many different 5-year labs. And so it's just really important, I feel, to have, a vibrant academic research ecosystem in the US and also in the world, because that often those early stage creative ideas are the things that lead to major breakthroughs and innovations. The whole of the deep learning revolution actually built on academic research from 30, 40 years ago. The inventions of neural networks and backpropagation and things like that are all, central to what we're doing even today and have been really important in the world. So, I advocate that we should have a vibrant academic funding model for academic research because the returns are quite large to society.
Yeah, excellent. And you and I and Dave Patterson and Joel Pinot are on the board of LAIR Institute,
Yep.
which was born in part out of a paper that you and Dave and I and a bunch of 7 other authors published called Shaping AI's Impact on Billions of Lives, where we advocated for the ways that AI research might impact society in areas like civic discourse and healthcare and science and job reskilling and journalism and more policy. And then we also advocated that there, in addition to things like 10xing down on NSF-style funding, we can explore and prototype other types of funding. So Laude Institute raises money from successful technologists who donate to Laude Institute, which is a nonprofit 501c3, which then in turn is running a moonshot grant program specifically dedicated to funding research labs, 3 to 5 year research labs with 3 to 5 PIs, 30 to 50 PhD students, targeting AI's impact on society in those areas I just said: scientific progress, healthcare, job reskilling, and civic discourse. And you've been an advocate for these alternative funding models as well, in addition to the traditional ones.
It was a lot of fun working on that paper with you and Dave and the many other co-authors we had. I think the thing I liked about that paper is we looked at a bunch of different areas where AI would have an impact. And some of them, if we get it right, will be amazingly positive impact. And other areas, it was a little less clear. There might be some negative consequences of AI. And what can we do overall across all these different areas to maximize the potential upside of AI, both from a technical computer science, research, ML perspective, but also in conjunction with policy makers and with people in those fields like health or education or scientists, and then also looked at the way in which we could all work together to sort of maximize those benefits and minimize the downside.
And specifically with research efforts that are in the 3 to 5 year time horizon that fit into a lab, which is in contrast to a lot of the hype we hear in AI right now, that like pursuing AGI or superintelligence contrasted to trying to help with medical, like success with frontline healthcare. Can you mitigate the drudgery that typical doctors feel, or eliminate obstacles that radiologists might have to actually using the technology that already exists? So I think it made it feel very much more real and specific and achievable.
Right. I really like the 3 to 5 year time horizon kind of thing with an ambitious sort of set of people around a particular kind of thing they're trying to achieve, because I feel like often that gets lots of different people working together with a mix of skills in order to sort of really push forward something. And it's not so distant that it won't have impact, but it's not so short a time period that you can't conceive of doing something ambitious, right? Even in my own career, I've tended to think of like, when I start on a new project, what could we do in 3 to 5 years? And I think that's a delightful time range to consider.
Nice. Yeah. And I'm wondering if you could share maybe some of your favorites. One thing I found while working with you on that paper that was always delightful is just how well connected you are to, seems like, dozens and dozens of bleeding edge projects by some of the most innovative thinkers and researchers and builders in the world. You both angel invest in them, and you are generous in donating your time and energy to advise ambitious impactful research projects that want to go make a difference from climate to science and civic discourse in healthcare. I think healthcare is one of your passions. On the program committee that we built for the Moonshot Grant program, which we now have all of our applications, including Turing Award winners and Nobel laureates and coverage from the top universities. So everything's working according to plan so far for funding some research that actually moves the needle on these areas of society. Curious, with your background and with exposure to so many active projects, if you could just share some of your, like one or two of your favorites.
Yeah, I mean, I think I am quite passionate about the application of AI to health in various ways. And I think the moonshot, if you like, would be how can we as society use every past decision that's been made in health to inform every future decision, right? And that's a super hard goal because there's all kinds of impediments to doing that. There's like very real privacy concerns. There's complicated regulatory requirements that differ for every jurisdiction. But I think if we kind of aspirationally try to say, what could we do so that we can learn from every past decision that's been made in a way that helps us have every clinician and every person themselves be informed and make better decisions in the future, that would be like a awesome, amazing goal. And I think, a 3 to 5 year moonshot around that might be able to make some progress to that. Probably can't get all the way there, but that would be pretty amazing even if it made it partway to that.
Is your sense that with the current capabilities of AI systems, the challenge for that would be more in the adapting the existing medical health records, legal considerations, and what the lawyers for insurance providers and the hospitals themselves, that might make it all sounds very hard, like more of an implementation challenge than the capabilities? Or do you think that the capabilities have a ways to go before we would get the benefits?
Yeah, I mean, I think there's a bunch of interesting technical researchy questions in there, but there are a bunch of kind of grungy, how would you get the data in the right form to be able to learn from it? Because it's in every different healthcare system, it's in slightly different forms and so on. You probably have to use things like privacy-preserving machine learning or federated learning or things like that. So how would you make that work on a technical perspective? Because you're not going to be able to move healthcare data from where it sits. Instead, you're going to need to be able to learn on the data in a privacy-preserving way in a whole bunch of different, environments. So there are real technical challenges, but there's also, as you say, legal and regulatory kinds of challenges as well. But, I think that's part of why you want to have a whole group of people thinking about these issues with different kinds of expertise. Right? Like you need some people with machine learning expertise and, computer systems building expertise, as well as legal and policy and regulatory expertise.
Yeah, makes a lot of sense. Any other projects that come to mind as a favorite?
I'm kind of enamored these days about how can we make our computing systems even more efficient than the latest cutting edge TPUs or GPUs. I feel like there's room there for interesting and innovative approaches for, much lower cost, say, inference, which seems like it's going to be a major thing in the world, even more than it already is.
Going back to the original 2013 napkin sketch for why TPUs should be born in the first place.
Yeah. I mean, if you redo that napkin sketch now, you're going to realize that we want, first, much lower latency systems than we have today. As well as much more throughput, and performance per watt is going to be a really important thing. So what can we do that would make way lower, energy systems that still provide the same quality and performance?
Mm-hmm. How do you see the relationship between all of the massive amount of research happening inside the Gemini team, inside DeepMind more at large, and now zooming out even one more layer to the AI ecosystem beyond Google, the relationship for the academic research and research happening beyond Google's bounds and what happens inside Google? Traditionally, things like the Transformer paper, like MapReduce, you've had these channels of exporting innovation outside of Google. I imagine you also have imported innovation and built on the shoulders of the giants outside, and that's why, like you gave examples already. Do you see that evolving these days as Google, with such a massive investment and such a leadership position in Gemini and in the hardware, kind of up and down the entire stack. Has it evolved, and does it need to continue to evolve, especially as we continue to face we're trying to innovate for funding models for the others, but it's not looking good, in my opinion, and I can't speak for you, but curious your thoughts on that dynamic, that relationship at the bound of Google and innovation happening in traditional mechanisms.
Yeah,
besides Google.
I think there's obviously continual evolution about publishing models and so on, or publishing characteristics. So I think in this current competitive dynamic, we tend to not publish the secret sauce inside our architecture of our Gemini model, say, but we do publish a lot of stuff in the sort of earlier stage research aspects of, here are interesting new kinds of model architectures that we haven't proven out, but we've experimented with at small scale to publish them so that the rest of the ecosystem can, pick up those ideas and explore them as well or build on them. And we also kind of look at the broader publishing happening in the rest of the community and sort of look at, how could we adapt some of those to some of the problems we're seeing. And I also don't think publishing has to be we publish it or we don't kind of thing. There's really a continuum there about when do we publish and what do we publish. So I'll give you an example. In the computational photography work that Google Research has been doing for many, many years, we have awesome researchers in that field. They often, almost annually come up with a really cool new thing that can go into the pixel camera software pipeline. Mm-hmm. So things like night sight or astrophotography or magic eraser, where you can erase like that person who wandered in front of your photo that you didn't want in the photo in the first place. And so what we tend to do there is we put it out into the next Pixel N+1 phone that's coming out. And then we sort of wait a little while, and then we submit a SIGGRAPH paper about the innovations that went into that feature. Mm-hmm. So it's sort of a little bit of a delay. We take advantage of it in our products first, and then we sort of let the rest of the community know about, what is happening underneath the covers, and they can build on it. So I think that's a pretty nice thing. Yeah. And there's this nice continuum of, not just the endpoints being choices.
Can you think of any off the top of your head examples of papers or ideas in that category you just mentioned of kind of the earlier, more experimental stuff where you are publishing, is either here at NeurIPS or happened recently that you're finding exciting and have been engaging with the outside Google? And I'd love to talk a little bit more about how it's been, how challenging it has been to organize inside Google, because it's an extremely impressive large organization, and I can imagine internal conferences even happening that would be a little tiny version of NeurIPS or something like that. But before you answer that one, I'm curious if you have any specific examples.
Yeah, just one off the top of my head. There was a paper published by some Google researchers here on kind of a hybrid between the transformer and recurrent models that's called Titan, I think is the name. So it's sort of looking at how can you have much longer context by using a recurrence relation, but using chunks of tokens rather than individual small tokens, and learning to kind of compress the sort of very porky representation of every token into something that's a little more compact, and then have a whole sequence of those that you use recurrent steps on. So that's just a good example of, that is not in our Gemini models. It could be in the future, but it does seem like an interesting idea to explore. One more thing on the internal. Every October.
Somebody told me about a conference. They're like going to a Google conference, and I was like, that sounds so cool.
We have a Google Research Conference. It has like 6,000 attendees every year.
And I know there's a sentiment, if you talk to the PhD students here, that the Google Research Conference might have papers that feel a year ahead of the papers you're seeing at NeurIPS, just because there is a gap between what's happening in the open and what's happening at Google. So I'm wondering, besides making a conference, how have you found it to sort of be able to build an organization that is so innovative and is able to generate the frontier, the state-of-the-art progress that we're all using?
I think one of the reasons the internal research conference might feel a little bit like that is often, for an external thing, you have to be quite far along in your research idea to get it accepted and published. And the internal conference, there's a whole range of maturity of the work. And so people are perfectly willing to have lightning sessions of like cool early stage results that aren't really fully baked yet. And you get like 10 of those in an hour session. So I think part of that is, yes, it hasn't been published externally, but also part of it is just trying to, circulate some of the ideas that are being explored with your colleagues. And it has to be a little less fully baked.
Yeah, no, I'm inspired by that. I feel like NeurIPS is really impressive, very large, and maybe there's room for that architecture of a conference to be exported as well in terms of innovation.
Yeah. I mean, the workshop days here feel a little bit more like that because it's earlier stage work and so on, but it's still a fairly traditional thing of like a PDF of some paper-like artifact. And here are often these things are just talks with a few slides or not necessarily a full paper that someone had to write up.
Cool. Yep. Okay, well, I think that's a wrap for us. Thanks for taking the time. Appreciate all your thoughts.
Thank you. Appreciate it. Thanks for having me.
Enjoy the rest of NeurIPS.
And it's beautiful here.
It is.